Welcome to lecture 7 on conic sections. So, in the last lecture we discussed about tangent and normal of a parabola. In this lecture we will describe the parametric form of parabola, and then we will discuss the tangent normal in terms of the parametric form. Parametric form of the parabola y square equal to 4 a x. So, note that this parabola x is always non-negative and y can be negative as well as positive. So, and as x you increase, then you get for every fixed x there are two values of y here, and as x goes from 0 to infinity, y takes values from, if you look at the upper half part of the parabola, y goes again from 0 to infinity, in the lower half it goes from 0 to negative infinity. Right. So, if we put y equal to t, where t is any real number. So, y can take value from minus infinity to positive infinity, then x is equal to y square by 4 a. So, this is equal to t square by 4 a. So, any general form, so any general point, so any general point on the parabola can be written as x is t square by 4 a and y is t. Now, instead of writing like this involves fraction t square by 4 a. Suppose we do not want this fraction, then we can put, so instead of y equal to t, if we use y equal to 2 a t. Note that a is positive. So, this again as t goes from minus infinity to infinity, y is also from minus infinity to infinity. So, then x will be equal to y square is 2 a t square by 4 a, that is 4 a square t square by 4 a, which is a times t square. So, we will write, we will use this as the parametric form. We will use x equal to a t square, y equal to 2 a t as the parametric form of the parabola y square equal to 4 a x. That is, any general point of the parabola y square equal to 4 x can be written as a t square 2 a t. So, the advantage of this is that we use only one parameter t to describe any point on the parabola. This already satisfies. If you write a general point as x 1 y 1, then you have to use one more equation, that y 1 square equal to 4 a x 1. So, this is the general point, and you can see that this at t equal to 0, you get the vertex 0 0. This is at t equal to 0. If t is any positive, then you get x equal to a t square, y equal to 2 a t, that means y is positive. So, this is point a t square 2 a t for t positive, and we have point a t square 2 a t for t negative. So, as you take t varying from minus infinity to infinity, you get a point on the parabola, and for every t you get only one point. So, as t varies between minus infinity and plus infinity, we get all points on the parabola. Also, there is a unique point a t square 2 a t on the parabola, for any given t. So, all the points can be uniquely represented as a t square 2 a t. Now, let us write the equation of the tangent and normal in terms of this parametric form. So, equation of tangent and normal in parametric form. Recall equation of tangent at point x 1 y 1 is given by y 1 equal to 2 a x plus x 1, and equation of normal at x 1 y 1 is given by y minus y 1 equal to the slope of tangent, you can see easily from this equation, is 2 a by y 1. So, slope of normal is minus y 1 by 2 a times x minus x 1. So, these are two equations of tangent and normal. Using x 1 y 1 equal to a t square 2 a t we get equation of tangent is y times y 1 is 280 equal to 2a x plus x 1 is 80 square. So, 2a cancels, this gives, that is t times y equal to x plus 80 square. So, this is a useful formula for tangent line at the point 80 square 280 is T y equal to x plus 80 square. Similarly, let us find equation of normal. We have y minus y 1. So, y minus 280 equal to minus y 1 is 280 divided by 2a times x minus x 1 is 80 square. That is y minus 280 equal to, this is equal to minus T x plus a t cube, which can be written as y plus T x equal to 280 plus 80 cube. If you look at the slope of the tangent line, this has slope 1 by t, and the slope of the normal line is minus 1 by t. So, in terms of this t, if t is not equal to 0, then we get slope of the tangent line is 1 by t, sorry, and slope of the normal line is minus t. This has slope minus t. Let us also find the equation of the chord joining two points, say P is a t 1 square 2 a t 1 and Q is the point a t 2 square 2 a t 2. So, if we have any 2 points on this parabola P and Q, we want the equation of the line joining this P and Q. So, that can be obtained as y minus 2 a t 1 is equal to slope, which is 2 a t 1 minus 2 a t 2, this is y 1 minus y 2 divided by x 1 minus x 2 is a t 1 square minus a t 2 square times x minus x 1 a t 1 square. That is y minus 2 a t 1 equal to, here I can cancel a and t 1 minus t 2. So, 2 divided by t 1 plus t 2 times x minus a t 1 square. So, multiplying by t 1 plus t 2, this gives t 1 plus t 2 times y minus 2 a t 1 times t 1 plus t 2 equal to 2 times x minus a t 1 square or y times t 1 plus t 2 equal to 2 a t 1 square plus 2 a t 1 t 2 plus 2 x minus 2 a t 1 square. 2 a t 1 square cancels and we get y times t 1 plus t 2 is equal to 2 times x plus a t 1 t 2. Let us record this formula. This is the equation of the line joining point a t 1 square 2 a t 1 and a t 2 square 2 a t 2. Next, let us look at point of intersection of tangents at two different points. On the parabola y square equal to 4 a x. So, let the points be P is a t 1 square 2 a t 1 and Q is a t 2 square 2 a t 2. Recall that in terms of this parametric form, the equation of tangent we have derived is T y equal to x plus a t square. So, the tangent at P is given by T 1 y equal to x plus a t 1 square and tangent at Q is given by T 2 y equal to x plus a t 2 square. Now, we can solve these two equations to find the point of intersections. So, to get the point of intersection, if we write this equation as 1, this is 2. So, 1 minus 2 will cancel x and we get t 1 minus t 2 times y equal to a times t 1 square minus t 2 square, which implies y is equal to a times t 1 plus t 2, and therefore, x from equation 1 is t 1 times y, t 1 y minus a t 1 square, which is a t 1 plus t 2 minus a t 1 square, which is equal to a t 1 t 2. So, the point of intersection is given by a t 1 t 2 comma a t 1 plus t 2. This formula again will be useful to remember. Point of intersection of two tangent is a t 1 t 2 comma a t 1 plus t 2. Now, let us look at few problems. So, the first problem that we will do is the following. So, if the tangents at points P and Q on a parabola meet at point T, prove that first T P and T Q subtend equal angles at the focus, we denote by S. Second, prove that S t square is equal to S p times S q. And third is that triangle S p t is similar to triangle S T Q. So, the first step is we try to draw the picture. Let me draw the picture here. We have this parabola. Suppose we take 2 points P and Q, P and Q. Then it says look at the tangent at P and tangent at Q. Suppose these tangents meet at a point T and we have focus S a comma 0, then we have to prove that T p and T q subtend equal angle at the focus. That means that let us draw this triangle and this triangle. So, we need to prove that this angle and this angle are equal. So, what we do is let us say let me use another color. So, let us draw perpendicular from T to this line S p and S q. Let us call this point as M, and on T q we have perpendicular M dash. Okay. So, we know that we can take the point in the parametric form. So, let P be a T 1 square 2 a T 1 and Q be the point a T 2 square 2 a T 2. Then we just derived the intersection of the tangent line. So, by the previous formula, for the point of intersection of tangent lines at P and Q, we have the coordinate of point T is given by a T 1 T 2 and A T 1 plus T 2. So, we have got the coordinate of point T. Now, let us write what is the equation of the line S P. We have this figure. So, line joining the focus to this point P, what is the equation of this line? Is y minus 0 equal to slope 2a t 1 minus 0 divided by a t 1 square minus a times x minus a, because S is the point a comma 0 and P is the point a t 1 square 2 a t 1. So, this gives y equal to two t 1 by t 1 square minus 1 times x minus a, that is t 1 square minus 1 times y minus 2 t 1 x plus 2 a t 1 equal to 0. Now, let M be the foot of perpendicular from T to the line joining S and P. Then what is the length of this perpendicular? Recall the perpendicular distance of a point x 1 y 1 to the line a x plus b y plus c equal to 0 is given by mod of a x 1 plus b y 1 plus c divided by square root of a square plus b square. So, therefore, we can calculate the distance T m. This is equal to, the equation of the line is given by this previous equation. So, we put x 1 y 1 as a t 1 square 2 a t 1 in this equation. This is equal to t 1 square minus 1 times y 1 sorry we put, this is the perpendicular draw from the point T. So, we put y 1 equal to a t 1 plus t 2, this is t 1 square minus 1 y 1 minus 2 t 1 x 1 minus 2 t 1 x 1 is a t 1 t 2 plus 2 a t 1, this in absolute value divided by square root of t 1 minus 1 square plus 2 T 1 square. So, if you simplify this, this is equal to A times A, we can take common from all this, and the denominator, if you see, this is T 1 minus 1 square plus 2 T 1 whole square, this will be this was T 1 square minus 1 square plus 2 T 1 square. This is T 1 square plus 1 whole square under square root. And the numerator is A times mod, we have T 1 square minus 1 times T 1 plus T 2 minus 2 T 1 square T 2 plus 2 T 1. Let us simplify it further. A times, we multiply this out. So, this is T 1 cube minus T 1 plus T 1 square T 2 minus T 2 minus 2 T 1 square T 2 plus 2 T 1 divided by denominator is T 1 square plus 1, which is equal to A times T 1 cube minus T 1 square T 2 and then plus T 1 minus T 2. Now, you can factor, and this is equal to A times T 1 minus T 2 times this was T 1 square plus 1 divided by T 1 square plus 1. This cancels and you get T m is equal to A times mod of T 1 minus T 2. So, this is the length of the perpendicular dropped from the point of intersection of the tangent to the line joining the focus to the point P. Since this is symmetric, with respect to T 1 and T 2, the distance T m dash, where m dash is the foot of perpendicular to the line S q, this is also equal to T m equal to A times mod T 1 minus T 2. So, T m is same as T m dash. Now, let us look at the picture again. We have a point Q here, this is a point P, the tangents meet at this point T here, and we have focus S. Line S P and S Q. This point is M and this point is m dash. So, what we have got is T m is equal to T m dash. We have T m equal to T m dash. What we had to prove, the first part was that T p and T q subtend equal angles at the focus S. That means that T p, this subtends this angle at the focus, and T q subtends this angle. We have to prove that these two angles are same. Right. What we have, T m and T m and T m dash are equal. Now, these two right angle triangle. So, triangle T m s and triangle T m dash s are congruent. Because both are right angle triangle with the common hypotenuse and T m equal to T m dash. So, this implies angle T s m is equal to angle T s m dash. That is same thing as saying the angle T s p is equal to angle T s q. This proves 1. The second part is to show that S t square equal to S p times S q. So, we have S t square equal to S p times S q. So, we need to find the distance. S has coordinate a comma 0, t is a t 1 t 2 comma a t 1 plus t 2. Now, to prove S t square is equal to S p times S q. Let us calculate what is the distance. This point P is a t 1 square 2 a t 1, q is a t 2 square. So, S p square is a t 1 square minus a square plus 2 a t 1 minus 0 square, which is equal to a square t 1 square minus 1 square plus 4 a square t 1 square, which is same thing as a square times t 1 square plus 1 whole square. So, therefore, S p is equal to a times t 1 square plus 1. Similarly, we have S q by replacing t 1 by t 2 is a t 2 square plus 1. And what is S t? Also S t square is equal to a t 1 t 2 minus a square plus a t 1 plus t 2 minus 0 square. So, this is equal to a square times t 1 t 2 minus 1 square plus t 1 plus t 2 whole square. which is equal to a square times T 1 square T 2 square plus 1 minus 2 T 1 T 2 plus T 1 square plus T 2 square plus 2 T 1 T 2. This 2 T 1 T 2 term cancels, and then this can be factorized as a square times T 1 square plus 1 times T 2 square plus 1, which is same thing as S p times S q. This proves the second statement. The third part was to show that triangle SPT is similar to triangle STQ. Next, to show triangle SPT is similar to triangle STQ. I will draw this again. This is point T, S is the focus. Triangle SPT is similar to triangle STQ. What we know is that these two angles, that TP and TQ subtends from part 1, these two angles are equal. So, if I call this angle theta, this is also theta. So, we have from 1 and 2 angle PST is equal to angle QST, and also we have ST square is SP times SQ. So, ST over SP, this is equal to SQ over ST. This is from this equation, ST square is SP times SQ, we can write like this. Therefore, we have this ratio ST over SQ in this triangle is same as the ratio ST over SP is same as SQ over ST. So, therefore, these triangles SPT is similar to triangle STQ. Okay, so we will do one more problem today. So, we have to prove that the area of the triangle formed by 3 points on a parabola is twice the area of the triangle formed by the tangents at these points. Solution. So, we can always assume that the equation of the parabola is y square equal to 4 x by choosing the vertex to be at origin and axis as the x axis, by choosing the vertex to be at 0 0 and axis, the axis as the x axis. So, we have parabola y square equal to 4 x, any 3 points we can take in parametric form. So, let P be a t 1 square 2 a t 1, Q is a t 2 square 2 a t 2, and R is a t 3 square 2 a t 3. Be any 3 points on the parabola. So, we need to find the area of the triangle formed by these 3 points. So, again recall how do we find what is the area of the triangle formed by vertices x 1 y 1, x 2 y 2 and x 3 y 3. So, how do we get this area? If we have any 3 points, coordinates x 1 y 1, x 2 y 2 and x 3 y 3. If we drop these perpendiculars, these are points P, Q and R, and let us call this as A, B and C. Area of the triangle PQR can be calculated by area of trapezium PABR plus area of the trapezium RBCQ minus area of trapezium PACQ. So, this area we wanted to calculate. So, for that we find the area of the two trapezium and then subtract this area. So, area of the trapezium can be calculated easily here. This is equal to half times, here these two are opposite sides of the trapezium of length y 1 and y 3. So, half y 1 plus y 3 times this distance here is x 3 minus x 1, x 3 minus x 1 plus half of this one will be y 2 plus y 3 times this distance is y x 2 minus x 3. Minus the area of this trapezium is half y 1 plus y 2 times this is x 2 minus x 1, and on simplification we get this area of the triangle is equal to half times x 1 times y 2 minus y 3 plus x 2 times y 3 minus y 1 plus x 3 times y 1 minus y 2. Easy way to remember this is equal to half of determinant of x 1, x 2, x 3, y 1, y 2, y 3, and the third column is 1, 1, 1. So, thus area of triangle PQR is equal to half times x 1, x 1 is a t 1 square times y 2 minus y 3. So, 2 a t 2 minus 2 a t 3 plus x 2 a t 2 square times y 3 minus y 1 2 a t 3 minus 2 a t 1 plus x 3 a t 3 square 2 a t 1 minus 2 a t 2, which is equal to 2 a square. If you take out 2 cancels with half. So, a square times t 1 square t 2 minus t 3 plus t 2 square t 3 minus t 1 plus t 3 square t 1 minus t 2, which is equal to minus a square times t 1 minus t 2, t 2 minus t 3, t 3 minus t 1. This is the area of the triangle formed by any 3 points on the parabola. Similarly, we have to find the area of the triangle formed by the tangents at these points. So, we know that point of intersection of tangent, points of intersection of tangents are given by a t 1 t 2, a t 1 plus t 2, if you take second and third point, then you get a t 2 t 3, a t 2 plus t 3, and first and third point will give a t 3 t 1, a t 3 plus t 1, and using the formula for the area, we can see that so area of the triangle formed by these tangents is equal to half of a T1 T2 a T2 minus a T1 plus a T2 T3. The difference in the y coordinate will be a T3 minus a T2 plus a T3 T1 times a T1 minus a T3, which if you simplify, this is equal to half of a square times T1 minus T2, T2 minus T3 and T1 minus T3, which is equal to half of area of PQR. So, this finishes today's lecture. In the next lecture, we will discuss about tangents and normal on ellipse and hyperbola, etc. Thank you.